Lecture 6, the Discrete Probability Distribution. This is part 1 of Lecture 6. Probability distribution is a listing of all outcomes of an experiment and the probability associated with each outcome. It actually looks very similar to a frequency distribution that we've seen back in Lecture 2. So what it entails is basically a listing of every single experiment's outcome and what is the probability of each of those outcomes. I'd say the best estimation is when we basically created the distribution for histograms and looked at the relative frequency. What are the characteristics of a probability distribution? So this is a general probability distribution. First, the probability of a particular outcome is between 0 and 1. The outcomes are mutually exclusive events. The list is exhaustive, so the sum of probabilities of the various events is equal to 1. So the example we're going to look through is basically tossing a coin 3 times, and we're interested in finding out the number of heads that are possible in the results. So we're going to be calculating the probability of heads. So what are the different possible outcomes for heads in the experiment? You can have 0 heads across the 3 coin tosses. You can have 1, you can have 2, or you can have 3. But before we go into the details of that, let's start by listing all of the possible outcomes. So first question is how many outcomes are actually possible? So recall from our previous lecture on counting, if every time the coin is tossed, there's 2 possible outcomes, heads or tails, if we're going to toss the coin 3 times, so we have 2 times 2 times 2, which says that we have 8 possible outcomes. The next step is to list all of those possible outcomes. One is all tails. So each time the coin is tossed, you get tails, tails, tails. This outcome lists that this is an experiment that has 0 heads. And we can list the rest of them. So here is all the different possible outcomes. So we have tails, tails, heads, tails, heads, tails, etc., all the way to the last one, which is heads, heads, heads. Now notice here we have the number of heads in each one of those 8 possible outcomes. So we could have 0 heads, 1 head, we can have 2 heads, or we can have 3 heads. So we are interested in finding out the probability for the number of heads. So let's go to the next slide. So here's a listing of all of the number of heads we could see in terms of the outcomes. So 0, 1, 2, and 3. What's the frequency of the outcomes? So in the previous chart we saw that 0 heads can occur once out of the 8 possible outcomes. 1 head occurs 3 times out of the 8 possible outcomes. 2 heads occurs 3 times, and 3 heads occurs 1 time, for a sum of 8 possible outcomes. What's the probability of each one of those outcomes? Well, the probability of 0 heads when the coin is tossed 3 times is 1 out of 8, or 0.125. 1 head, it's 0.375. 2 heads is 0.375. And 3 heads is 1.85. And as the rule states that since the events are mutually exclusive, and this is collectively exhaustive list, that the probability of tossing a coin and getting any one of these outcomes is 8 out of 8, or 100%. This is basically a graph here to represent, or a bar chart to represent the possibilities of the outcomes. Now notice this is a bar chart and the bars are not touching. Therefore, this is suggesting that these events are discrete events. So we can see that the highest likelihood event is either you roll heads twice or once. So if we were to characterize this distribution and try to figure out what is the center or the most likely outcome, we can pretty much guess that the most likely outcome is somewhere here at the top of the distribution, or 1.5 heads. And we'll prove this in a few slides. First, we want to define random variables. A random variables in an experiment of chance, the outcome occur randomly and are therefore called random variables. A random variable is a quantity resulting from an experiment that by chance can assume different values. A random variable is usually written as x, and this is a variable whose possible values are numerical outcomes of a random phenomenon. There are two types of random variables, discrete and continuous. In this chapter, we are concentrating on discrete random variables, and in Lecture 7, or Chapter 7 of your text, we'll be concentrating on continuous variables. So discrete random variables is one in which you may only take a countable number of distinct values, such as 0, 1, 2, 3, 4, etc. If the random variable can take only a finite number of distinct values, then it must be discrete. So examples of discrete variables include number of children in a family, bedrooms in a home, the number of heads appearing when a coin is tossed 3 times. Finding the mean of a discrete probability distribution. So the mean, otherwise known as the expected value or the expected return of a discrete probability distribution, is found by taking the sum of each variable x, multiplying it by the probability of that specific outcome, and basically adding that up. So that's going to give us the mean of the discrete probability distribution. Let's have a look at our example. So here we start off again with the number of heads in our experiment. Then we'll add in the probability of each of those outcomes that we calculated previously. Okay, and now we're going to take each outcome x, multiply it by that probability. And notice we get this listing. When we take these values and we add them up, we get the mean. So each x times p of x is then summed, so 0 plus 0.375 plus 0.75 plus 0.375, we get a mean of 1.5. Now how do we interpret this? This says that every time the experiment is conducted, so 3 coin tosses, we expect to get 1.5 heads. Now that obviously is not a possible outcome, because if a coin is tossed, you're either going to get 1 or 2, never 1.5. So we can adjust this. We could say after 100 repetitions, meaning after the coin is tossed 300 times, we expect to get 150 heads, which is simply the mean of the 3 coin tosses times 100. And now this outcome of 150 is a possibility. The variance and standard deviation of the discrete probability distribution. So for the variance, we basically take every single value x, we subtract the mean of the distribution and square it, just like we did before, and then we multiply each of those by the probability of x, and then we sum across. And of course, the standard deviation is the square root of the variance. So once again, this table lists the number of heads outcomes, the probability of outcome p of x. Now we can take each x, multiply by p of x, and once we do that, add everything up, we get the mean, which was 1.5. Now let's take the mean of each x and subtract the mean to get the deviation from the mean. And here's all our deviations from the mean. And finally, we square each of these deviations. So we have 2.25, 0.25, 0.25, and 2.25. And then we're going to take each of these deviations squared and multiply them by the probability of x. And therefore we get 2.25 times 0.125, etc. And the sum is 0.75. So the variance of this distribution is 0.75 heads, and the standard deviation is 0.6. So we would say in this experiment, the probability of heads. When you toss a coin 3 times, we expect to see 1.5 heads with a standard deviation or an average deviation from the mean of 0.86 heads. Let's do one more example. Second example. John Ragsdale sells new cars for Pelican Ford. John usually sells the largest number of cars on Saturday. He's developed the following probability number of cars he expects to sell on a particular Saturday. We're going to have to find the mean, or the expected number of cars he expects to sell on a given Saturday, the variance, and the standard deviation of this distribution. Now, You may ask the question, is 4 the maximum amount of cars that he can sell? Why don't we have 5 or 6? Well, let's think of it this way. There may be some kind of rule in the car dealership that you cannot sell more than 4 cars on any given day, and therefore he hasn't assessed any probability, or he's never in the past sold more than 4 cars in a given day. So here in this case, we're using this discrete probability distribution because notice that the number of cars you sell is a discrete value. It is not a continuous value. Now, the next slide here will actually be a video showing you how to solve this problem step by step. Okay, let's start off by drawing our table. So we have x, which is 0, 1, 2, 3, and 4. We have the probability of each x, which is 0.1, 0.2, 0.3, 0.3, and 0.1. Now, in order to get the mean, or the expected number of cars that he expects to sell on a particular Saturday, we have to take each x and multiply it by the probability of that specific outcome. So we have 0 times 0.1, which is 0, 1 times 0.2, 2 times 0.3, 3 times 0.3, and 4 times 0.1. So to get the mean, or the expected return, or E of x, of this experiment, we just add up x times P of x and get 2.1. So basically what we would assess here is that on any given Saturday, he expects to sell 2.1 cars. Now let's continue and find the standard deviation of this distribution. So the next thing we have to do is we're going to take each x and subtract the mean, or the expected return. So we have 0 minus 2.1, which is negative 2.1. Okay, let's fill in the rest. So we have negative 1.1, negative 0.01, 0.9, and 1.9. So now that we have that, we're going to take each of those and square that. So we have x minus the mean squared. And so we have 4.41, 1.21, 0.01, 0.81, and 3.61. Finally, we're going to take each of these squared values here, and we're going to multiply it by the probability of x. So our last column here will be x minus the mean squared times P of x. So our first value will be 4.41 times 0.1, which is 0.441. And we replicate that for the rest of our data. Okay, so now finally, in order to get the variance, we just sum this column and we get 1.29. The standard deviation is simply the square root of 1.29, which equals 1.14 approximately. So that's how we find the mean and the standard deviation of a discrete probability distribution. Okay, and here's the results, in case you want to spend a little bit of time, pause it, and check your work. All right. Well, that's the end of part 1 of lecture 6. Please move on to part 2.